Marks. I work on Java at Oracle. And there's my Twitter handle. I work on core libraries, but this talk is actually about language features that we are working on in the JDK group. Now, I don't really want to talk the Oracle Safe Harbor slide, but I do want to spend a moment here saying that there's some things mixed into this this session, which are very futures oriented. And so I'm going to put some code up that is speculative. We will be changing the syntax. It will be about features that are currently under design and development. So that said, I will try to delineate what things are in shipping releases and what things are futures. Okay, so with OpenJDK, OpenJDK is a large umbrella project that has a whole bunch of activity going on in it. And so I think the biggest project in OpenJDK is the JDK itself. As you know, we just shipped JDK 14, and we are in a 6-month release cadence to ship JDK 15, JDK 16, and so forth. And that includes lots of features, APIs, performance improvements, quality improvements, et cetera. So there's a lot of work going on there. There are also several other long-term projects which are not connected to any JDK release. And these might be ones that you've heard of. There's Valhalla, which is covering value types, Loom, which will be introducing virtual threads, formerly known as fibers, Panama, which is dealing with native interfaces and functions, and also there's some vectorization work. And the subject of today's talk is Project Amber, which is adding new features to the Java programming language to improve programmer productivity. Now, there are other talks and materials out there about those other projects. So for today's talk, we're just going to be talking about Project Amber. All right, so these are the main features that are part of Project Amber. There are 6 features here, and some of them have been shipped already and some have not. I will go through these, but basically there's local variable type inference, otherwise known as var, text blocks, which some people call multi-line strings. I think that's a primary use case for it. Switch expressions, records, sealed types, and some enhancements to instance of that that will lead towards pattern matching. Okay, so the local variable type inference, otherwise known as var, was delivered in Java 10. So that was actually, I'm not sure the dates at this point, but that was sometime in the past. So anybody who's on Java 10 or anything later can use var. And it's interesting to see that the use of var has crept into code I'm seeing all over the place. Switch expressions went through a couple preview rounds of preview in the previous Java releases, but they were delivered in final form in Java 14 just last week, if I'm not mistaken. Now, I mentioned preview there. There are some other things going on here with text blocks, records, and the pattern matching for instance of enhancement. Those are what we call preview features in Java 14. And I'm going to cover what we mean by preview in a moment. And then sealed types is a little bit farther off in the future. There are a bunch of proposals and designs floating around for that, but that is not, the prototypes for that are not yet available in any JDK build, even an early access build. I don't think they are. I don't think they are available yet. Now, all right, so we have half a dozen or so different features. Are they all independent features? Local variable type inference and text blocks kind of are. Those are the most, I think those are among the most requested features we've gotten, so we went and added those, but those are largely independent of anything else. These last 4 features I think are very interesting because they look like they're completely different, right? So we're working on switch expressions, we're working on records, which are a new kind of class, working on some instance of stuff. These are all, they all seem like they're independent features, but really they are all part of a larger strategy that is heading towards a programming language concept called pattern matching. And so what I will do in this talk is run through all of these features very quickly, and then towards the end I will try to pull it all together and show how these last 4 features are working together and give you a flavor of what we are going to deliver in the future with pattern matching. Okay. A little bit ago, I mentioned preview features. So one of the things that people were concerned about, including people who work on the JDK itself, is if we have a 6-month release, deal? How can you possibly develop and deliver a feature that takes longer than 6 months? And um, the fact that we're releasing JDK versions every 6 months doesn't mean that all the development for that release have to fit into the preceding 6 months. And so the problem, though, is that there's really hardly any opportunity to have what we used to call things like beta releases, because the, the general availability or GA releases come out every 6 months, and so how can you deliver um, a feature that's not complete in a Java release? Because our commitment to Java is for uh, for very, very strong compatibility. But if we want to deliver something that is not quite done, then how do we do that? So the preview mechanism is a way of dealing with that. And so in a Java GA release, a general availability release, certainly it has its full features that are finalized and standardized and well specified. But they're also what we call preview features. And so they are also fully specified and implemented, but they are still subject to change as people get use of them. And so the point of putting these into a GA release is putting these into everybody's hands. And so if you want to try it out, you can enable preview features and go ahead and try to use that preview code. Now, there's some extra work you need to do in order to use preview features. So you have to enable preview features both at compile time and at runtime. And so you do that by passing these extra flags here, minus minus enable preview. Now, the reason for that is since these features are subject to change, including incompatible changes, we don't want people depending on them for their production use, unless they are, because if you're, if for instance you're depending on a preview feature in Java 14, if you accidentally put some of that into your production code, when you upgrade to Java 15, then that might break your code. So the idea is to specifically require an opt-in to say, okay, yes, I know I'm using a preview feature that is specific to Java 14, and I'm prepared to change my code to update it when we move on to the next release. So that's what the preview mechanism is. Most of these features have gone through at least 2 rounds of preview. Um, and some of them are still currently in preview and may end up going through several more preview releases before becoming finalized. All right, so now I'm going to get into the section of the talk where I click through these features, click through the 6 Amber features fairly quickly. I'm not going to spend too much detail I'm not going to talk about too much detail on most of these. I think there's there's not enough time to do every one of these justice, so I'm just going to hit the highlights of each of these. Okay, so the first feature is local variable type inference. Most often people just call this var because it replaces your variable declarations. In the variable declarations, instead of declaring a type explicitly, we use var instead. And so one of the things that we hear fairly often when people confront this for the first time is, oh, Java is turning into JavaScript. No, this is not true. JavaScript is a completely different language. It is dynamically typed. Java is still statically typed. Even though we're using var, it might look a little bit like JavaScript, but it is still different from JavaScript. In particular, Java is still statically typed, and the type of a variable declared with var is inferred, but it is inferred statically at compile time. And so now here the question is, when should you use var? And the answer is, um, even though Java is statically typed, we've started to realize that declaring an explicit type every time, everywhere, isn't necessarily the best thing. In particular, sometimes variables type is not very important in some particular context, and in fact adds clutter. And so in those cases, you can replace the type declaration with var. So let me show an example of that here. So this is a try with resources statement where we have a socket and we want to read a line of text from it. But we have to go through several steps to do this. From the socket, we get an input stream and store that in a variable. And then we wrap that in an input stream reader and store that in another variable. And then wrap that in a buffered reader. And then finally, we use the buffered reader within the try with resources block. And so if you'll notice, there's a lot of redundancy here. In every declaration, um, the same name is repeated on the left side and the right side. So we're getting an input stream out of a socket. What do we get out of that? Well, that's pretty obviously an input stream. So that type declaration isn't doing very much for us there. Now we wrap that in an input stream reader. What type do we get out of that? Well, we get an input stream reader, and same with buffered reader. So the type declarations are really sort of getting in the way here. And in fact, they make the lines longer and they add clutter to the declarations. So here I've replaced the declarations with var. And notice certainly it makes the lines shorter. We can fit everything on one line. And in fact, we don't really care all that much about the exact type of well, we might care about the type. We don't care about the declaration of the type. So the only thing that's actually used in the body of the try with resources is the buffered reader. And I've given the variable name an evocative name. If I'm using this within there, there's something called buff reader. Oh, well, that's the buffered reader I just created above. That's clearly true. So the type declaration is really sort of getting in the way here. And so in those cases, it's really good to use var to have the compiler infer the type for you instead of having to write it out every time. All right, moving forward, text blocks. So I think the easiest way to explain text blocks is as a two-dimensional string literal. If you want to put string literal into a Java program that uses multiple lines, you have to do you have to put escape sequences in and repeated appending using the plus operator. And that's kind of a pain. Many IDEs will support this for you. So if you paste in some text, you get some nice behavior there, but it really adds a lot of clutter to the resulting source code. And I'll show this on the next slide. But editing and maintaining such a thing is pretty painful. One of the features of text blocks is that and I think one of the things that took the longest amount of time is coming up with policy for what we call incidental white space. And the main thing there is that we don't want incidental white space to be part of the actual string literal. And then along with text blocks, we added a few new APIs in support of this to the string class. But let me show an example here. So let's say we just have a simple code block here that we want to write a chunk of HTML. And so the typical way to do this is to put each line in its own string literal. And at the end of every string literal, we had to put a new line escape. And then we had to append that with the plus operator. And so you can see that there's a lot of syntactic noise here with the quotes at each end of the line and the escape sequences and the plus. And it's very easy to miss that. And so it just requires a lot of keyboarding if you want to change the body of the text. And so this is what a text block looks like. So this is delimited by triple double quotes, and the new lines inside here are part of the string literal. There's some special case rules, and in fact, there are rather a lot of special case rules, but for the most part, this does the right thing. So we have this is a multi-line string literal. It includes the new lines. One of the things is, though, that we want Java to be platform independent. And certainly things like Linux and Windows have different line end conventions. So what happens if you take this code from, say, Linux to Windows, what happens to the new lines? Well, we've somewhat arbitrarily decided that the new line separator is the NL character, the line feed character, as opposed to carriage return line feed. And that is a bit of a disadvantage to Windows, but we felt we had to do that because if you were to take this and recompile on Windows, you would not want um, you would not want the string literal to embed the line ending conventions of the operating system that it happened to be compiled on. So there are ways to, there are easy ways to replace the line end conventions with something else using string APIs if you need to do that. In any case, there's something else going on here, which is, what about the leading space at the beginning of the line? The line ends are part of the string literal, but what about the leading space? So our approach here is to say the stuff at the very left part of the string um, before the leftmost line is what we call incidental white space, and it's stripped away. And so if you go look at the JEP or the specification, um, it's actually fairly complicated rules. But basically, what it does is it determines this rectangle here, which I've illustrated using these colored dots. And the reason for this is, if you go in and suppose you paste this code somewhere else and it happens to be at a greater level of indentation, you don't want the string literal that results to have a different value because of this incidental white space. So the compiler has a rule built into it about determining what incidental white space is. So there is no white space to the left of the HTML tag, but there is white space to the left of the body tag, and that is the white space that that pushes it to the right relative to where the HTML tag begins. So the incidental white space is that rectangle there that forms the left, going all the way from the actual left margin to the left margin of the text block. And so this is why we call it a two-dimensional um, uh, two-dimensional string literal. It is not merely a multi-line string literal. So there's a lot of intelligence built in here. And we think that in actual use, even though these rules are pretty complicated, in actual use, this ends up doing the right thing most of the time. All right, I'm gonna keep moving here, clicking through the various Amber features. So switch is a venerable statement. It originated in the C programming language, and it was mostly carried over to Java. There are some changes relative to C, but Java's switch is a very old construct, and it's basically a statement that has stylized go-tos in it. And so at the top of the switch is like a go-to to a particular case label, and then a convention is to use break at the end of every case block. They're not actually blocks, which is another thing, but you can put break in there, which is an implicit go-to to the end of the switch. So it's very much a control construct with some implicit go-to behavior in it. But for the most part, I mean, there are some weird special cases, and people take advantage of this. But mostly, people put break at the end of every sequence of statements following a case label, and it's easy to forget putting in the break case. Often, what's done is you want to have a variable and you want to assign something to it in each case. If you forget to do that, you've made an error, and you don't find out about that until runtime. And so if you accidentally omit a case, suppose you have a set of values that you know is restricted, and you accidentally forget to add one of those cases. Well, the switch statement will happily say, oh, you didn't provide a switch for that, you must not care about it, and so it will simply skip over it and do nothing for you. So I know when Brian Getz has given talks about this, he says this is the language daring you to make a mistake. And if you look at the switch statement, there are a lot of things you can get wrong very easily. And the problem with getting things wrong in this case is that often those do not result in compiler errors. So you have to do some debugging at runtime in case something goes wrong. So what we've done is we said, it seems like in most cases, switch is better off as an expression instead of a statement. And so A statement is about control flow. We start at the top, we go to a case label, and then break goes to the end. An expression is a sequence of tokens that is evaluated somehow and then produces a value. And most often, it is easiest to have just one, just for each case. There's often not a need to have multiple statements in there. And so the requirement to put break everywhere is kind of a problem. So we've introduced this new label form using an arrow to say, okay, so the value of this expression in this case is a simpler expression. And so that way we can avoid having to do a break statement everywhere. Now, this is the same arrow token as is used in a lambda expression, but this arrow does not mean that it is a lambda expression. And so I'll show this on the next slide. I'll go through some code example here. One thing about expressions, though, is that an expression always needs to produce a value, or it needs to throw an exception. So in that sense, we say the expression must be exhaustive. If, for instance, you're doing a switch over an enum, you must handle all the cases or provide a default. And so one of the nice things about the switch expression is the compiler can check this for you. So let's go to the code example here. So this is kind of a typical this is a switch statement here. This is kind of a typical old code. And the example is a bit silly, but let's assume we have an enum, which is the days of the week. And we want to switch over that and assign a value to a variable, which is the number of letters. And so for Monday, Friday, and Sunday, the number of letters is 6. Oh, and then we have to break. And then on Tuesday, we have the number of letters is 7. You can see what's going on here. And so if you look at this statement, there's this pattern here, which is num letters is assigned exactly once in every case. And if you forget that, then you have a bug in your program. Now, you also have to put a break after that. You can't just assign it and move on. If you forget the break, then the switch statement falls through to the next one, and the next statement will get executed and will erase the assignment that you just made. So that's another bug. So you have to remember to put break everywhere. And then, so there are only 7 days of the week, and our putative enum declaration has 7 days. But we're still forced to put in this default statement here that says, oh, in case somebody adds another day of the week, we throw an exception that is never going to be thrown. So it's like, but we're forced to put this in. So let's turn this into an expression. So here, now notice the switch is on the right-hand side of an assignment statement. And so we are now also using the arrow form. So on the right side of the arrow, again, this is not a lambda expression, but it sort of looks like a lambda expression where what's to the right of the arrow can be a simple expression. And so in this case, it's just constants. We just say case Monday, Friday, and Sunday, and the value for those cases is 6, and then Tuesday 7, and so forth. And so that's pretty nice. It makes it a lot more concise. But there's something subtle going on here as well, which is we have covered all of the enum values. And so we don't need to put a default case in. And so there's something really subtle going on here, which is sometimes in a switch statement, you want to handle some of the cases, but not all. And if that happens, that's okay. Or you can put in a default, which is to handle all the rest of the cases. But exhaustiveness allows you to say something slightly different here, which is, I want to handle each case explicitly, and this switch is intended to cover all of the potential values. And Now, it's not going to happen with days of the week, but if somebody were to come along and add a new enum value, you would want this to error out because the intent of this switch expression is to cover all of the cases explicitly. So if you had a default in here, then that would sort of accidentally end up getting invoked if somebody were to add a new enum value. And so that's a source for bugs. So if somebody were to add an enum value somewhere, you'd have to carefully inspect every switch statement to make sure that it was handled properly. And with switch expressions, the compiler will tell you if you've made an error by leaving one out. Okay, moving on. Records. All right, so record. Let me see if I can describe this very quickly here. Um, it's a class. It's a data aggregate, it's basically just a collection of fields, and those fields have names and types, and also the language, if you have a field with a given name, the language will provide for you a public accessor method with the same name. And we'll see this in action a little bit later. Um, but one way to think about a record is like a nominal tuple. And so in some languages have a tuple where you can have an aggregation of arbitrary data, which is unnamed. And we've been asked about that a lot. We've thought about tuples a lot. And one of the things about Java is that we do like things to have names. And you can see this in other languages sometimes. If you if you have a tuple, it's basically a very short sequence, and sometimes you need to name those things. So some languages implicitly number them. So it's like, well, I want tuple value 0 or tuple value 1 to extract the components of a tuple, or sometimes it's left and right or something like that. You end up coming up with sooner or later, if you have unnamed tuples, then you end up having to use names that actually do not mean anything. And so it's not to say that unnamed tuples are not useful, but in thinking about that a lot, we decided we did not want to follow that approach in Java. And so records are a way of providing what we're calling nominal tuples. And so the fields have names. And so you can use those names, and when you give something a name, then you uh, clearly you should give it a name that has some meaning to the program. And I'll have an example later that shows that fairly well. But keeping to the fundamentals for a moment, so record is a class, but it's a class with um, it's an interesting flavor. There's some restrictions, but there are also enhancements. You declare the fields of a record, but common methods like equals hash code and strings are toString are provided automatically by the compiler. Now you can override them if you want to do something else, but the convention is simply to let the compiler provide those for you, and it will generally do the right thing. You can also write a constructor and override it if you want to do argument validation before initializing fields. This is very important. You don't necessarily want to allow fields to have any value. You might want to have argument validation. You can add additional methods to a record, and you can implement interfaces, and of course you will need to provide implementations of the methods defined by those interfaces. But the main point here is that implicitly, if you have a field, then there is also an accessor method of the same name, and so that is public, and that is a very strong notion that goes throughout records. I want to talk about a couple of restrictions as well, which is records cannot be subclassed. So record implicitly is a subclass of java.lang.record, and it is final by default. So I can declare a record, and there's a long there were many discussions about this. Subclassing is very powerful, but it also tremendously complicates things. I know there are many discussions on the internet about how to properly write an equals method, and in Java. And equals by itself on a individual class is not that difficult. But if you want to write an equals method and handle arbitrary subclassing, then things get complicated. You can get into big arguments about whether equals should be based on get class or instance of, how you deal with subclasses that might add state and so forth. And um, we decided that just to keep things simple, we would disallow subclassing. It really makes the semantics of equals much, much stronger. In addition, there's this notion here of decapitation. If we were to allow subtypes of records that added new fields, then upcasting in Java occurs um, quite implicitly. And so you might want to copy a record by looking at its fields and creating a new record from that. But what that accidentally does is leaves state behind from subclasses. And so sometimes that's referred to as decapitation because it takes all the state from the superclass, but not from the subclass. And that is an extremely subtle error. And so that's something that is also avoided by restricting subclasses. So the idea is that when you declare fields in a record, those fields form the complete state of the record. And so what you see is what you get. And so you know that somebody hasn't subclassed it and added some additional state that you can't see. So another restriction is that records are immutable. More precisely, they are shallowly immutable. That is, all fields are implicitly final. Now, you can have a field that is a reference to a mutable object. So it's still the case that from a deep perspective, records are not immutable, but the fields are final. And this is the design decision we made that's basically forward-looking. I know there's a lot of demand for saying, well, gee, if record fields were mutable, then they'd be much more useful for these cases. But that would actually cut off some future enhancements. That would make future enhancements regarding pattern matching and deconstruction, which I will cover later. That would make those enhancements more difficult. Anyway, record fields are implicitly all final. All right, so let's look at a code example here. So this is a conventional Java class is intended to represent a point with integer coordinates x and y. And so you can see in the upper left the the significant parts of this class are its name, point, and their two fields, int x and int y, and they're final because we don't want anything changing them. Okay, so that's all well and good, but what's all this rest of this stuff? Well, if you want to create a point, you need to write out a constructor. So you have to write a constructor that takes the arguments and then assigns them to the fields. Now you have to write an equals method. Otherwise, if you inherit equals from object, then you get identity comparison, which is probably not what you want. Two different points with the same x and y values should be considered equal. So you actually have to go through a fair amount of work to write a correct equals method. So this is actually fairly complicated. What I was saying earlier about subclassing makes this even more complicated. But even without subclassing, you have to write a fair amount of code to write a correct equals method. Hash code. Well, if you're going to put one of these into a hash map, then you also need to provide a hash code. And so you have to write that out as well. And then toString isn't required, but it is kind of nice because a point is a value, and so you might want to print out its values instead of having the system generated one for you. And then finally, there are a couple accessor methods that you have to write out, and all they do is return the values of the fields. So that's a lot of code, right? So I had to write it really small and put it into 2 columns. And that's a lot of code to support a point which just has 2 fields that otherwise has really no interesting behavior. So if you want to write this as a record, you just say record point int x int y, and then braces, and that's it. So this is not an abbreviation. This is the actual complete source code of a record, and this is pretty much equivalent to the code on the previous slide. So all of those methods, especially the kind of complicated ones like equals in particular, but equals, hash code, and string, and the accessors. Component accessors are provided automatically by the compiler. So if you look at this, this has two final fields, int x and int y, and it also has public methods, public method x that returns an int, and public method y that returns an int. So how would you use this in practice? So this is an interesting thing. So it comes up. I mean, it comes up in a whole bunch of places, but I wanted to pull this example out and highlight it because I think it's particularly interesting. Um, Sometimes in a stream pipeline, what you want to do is you're sending a bunch of elements through a stream, and sometimes you want to have an intermediate computation that you want to store and use in a later pipeline stage. And this is actually kind of a problem with streams. So in this case, let's say we have a list of persons and we want to sort them by score and then take the top n of them. But we want a list of persons. We don't want a list of scores. And so there's this problem here, which is we want to compute the score and sort by them, but then we want to just end up with a person at the end. And so there's a need here in the middle of this pipeline to have an aggregate that is a combination of a person and a score. And so this is one of the reasons people say things like, oh, well, if Java only had tuples, then we could do something like this. Well, we sort of do have tuples, and you can introduce a tuple here, or a nominal tuple, using a record. And so this is something that's a bit obscure. In regular Java, going back all the way to, I shouldn't say regular Java. This local classes have been a very old feature. I think they in JDK 1.1, local classes were introduced along with inner classes and nested classes. So it's possible to write a class declaration inside of a method. Now, it turns out nobody does this because a class declaration is a pretty heavyweight declaration. And so suppose you wanted to write a class that is basically a temporary class that holds a combination of a person and a score. Well, you could write a class, and then you'd write a constructor, and then you'd write an accessor for a person, and then you'd write an accessor for score, or you'd use direct field access or something. But it would actually, the class declaration you'd write out would be longer than the stream pipeline in the rest of the method. And so as a result, local classes are not used very much at all. I've been programming Java for, gosh, I don't know, decades. And I think I've used local classes once or twice. So it's just something that the feature is there, but it's really not all that useful because a class declaration is so heavyweight. And it's not the class itself, it's just that if you need to provide a constructor and accessor methods, then it starts to get pretty verbose. So a record is just a class. So you can declare a local record along with just like you could declare a local class. But since a record defines the constructor and accessor methods for you, it's a one-liner. So I want this thing here, and you have to give it a name, person X in this example, but basically this is a simple aggregate that contains a person and a score. So now we run through this, and we have our stream of persons. We create our new aggregate containing the person and the person's score, sort by the score, limit the number of elements in the pipeline, and then from our person record, we extract the person and collect those into a list. And so I think this is a really interesting use case for records because it almost gives you something that is very concise to use, kind of like tuples, except that the fields have names instead of first, second, left, right, A, B, or whatever. So I think that's a really interesting example for using records. And there are lots and lots of other examples, but unfortunately, I have to move on at this point. Okay, sealed types. So a sealed type is a new mechanism we are working on. It's not yet in preview, but there's been a bunch of discussions on this and design proposals. But the idea is to allow a class to control its subclasses. So there are existing mechanisms that do this. You can declare a class final. That means that cannot be subclassed. And we do use that in a couple places in the JDK. Um, but this is a big hammer because it prevents all subclassing. So even within the library, you can't write a subclass. And sometimes you want to do that. Sometimes you want to write subclasses, but restrict subclassing to only subclasses that you know about. And so that's what sealed types gives you. Now, we have sort of a workaround in Java already, and you see this fairly often. If you provide only package private constructors, uh, then um, then that means that you cannot write a subclass that is outside of the current package. And that more or less works, but it doesn't quite work because, um, well, one issue is that it works only with classes. It does not work with interfaces. So you cannot have an interface that restricts subclassing. And there's sometimes when you might like to have a public constructor, but there's a problem where um, um, if you have a public constructor, that implicitly means that you allow public subclassing as well, if it's a non-final class. And in fact, we've made some mistakes in the JDK in the past where we accidentally had a public constructor, and so it allows subclassing that isn't useful, and in fact could be considered an error. So really, there's no explicit language support for having a class that controls its subclass. Oh, so an example of the package private constructor is enumset. So in Java util enumset, if you look at the Java doc, there are no constructors visible because they're all private. But if you look in the source code, you will find that there are two subclasses in java.util named regular enumset and jumbo enumset. And those work because enumset has a package private constructor that its subclasses can call. So restricting subclasses to java.util. So with sealed types, the idea is to allow the class author to say, I want to allow only specific subclasses or interface implementations to exist. And so when you write a sealed class, the compiler, enough information is, well, this is checked by the compiler, but enough information is written into the class files so that the VM enforces this as well. So this is done in a couple ways. There's a new, the new proposal is to add a new permits clause to a class, or if you don't write out a permits clause explicitly, then the compiler will infer members of the permits clause to basically every type that is compiled in the same file. So let me show you what that looks like. So here, it turns out I'm using records as the example for no particular reason. This works well with regular classes as well as interfaces. Um, but we have our point record, which we saw earlier, and now we're declaring a sealed interface shape that has nothing in it except that it says it permits only two implementations, circle and rect. And then right below, we see a record circle that has a center and a radius, and that implements shape. And a rect has 2 points determining the corners of the rectangle, and that also implements shape. And so it's very nice. Just by looking at these declarations, you know that there's a little class hierarchy here that cannot be extended. So if you write code that uses a shape, you know it's either a circle or a rectangle. And you 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 there's never a case where some third-party code, writes some class that happens to implement the shape interface and does something different from what you expect. And so that's very powerful. We just have 4 declarations on here, and we can already make a bunch of interesting assertions about the type hierarchy. So here's a variant of the previous thing. We can just say sealed interface shape and not write a permits clause. And so in this case, the permits clause is inferred. And the formal definition is that the permits clause is inferred to have types that are declared in this compilation unit, where compilation unit is typically a file. But we expect this will often be used for declarations that are nested. So in this case, we have circle and rect, which are nested types within shape. And obviously, if you have something that is nested, it has to be in the same compilation unit. So we kind of expect this pattern to be very common. So the shape interface is what outsiders see, and then we might have internal implementations inside of shape. And so shape knows that it has restricted the implementations to known implementations in this class. Okay, one final thing before I try to wrap this up and show our future directions. Pattern matching for instance of. So in an instance of expression, um, you're doing a type test. So here we have typical classic Java code. Object, if the object is an instance of integer, what are we going to do with that knowledge? Well, we can cast it to integer and then use one of the methods of the integer type. Okay, and that's nice, but notice we had to write the type twice, and then in order to do the cast, either we had to add a couple extra levels of parenthesis, or we had to declare, an alternative way is to declare yet another local variable, and this tends to get in the way. But one of the observations is this pattern is very, very common. Do an instance of check, and if that instance of check is true, we do a cast to the exact same thing you just did an instance of. So we've decided to enhance the instance of expression to allow a variable name afterwards. And what this does is it implicitly introduces a new local variable that has the same type that you are testing for, what the type test is, and it is initialized to the um, to the result of casting, doing that cast that we saw on the previous slide. And so if you look at existing Java code, probably 90% of the casts are after instance of, and so this will get rid of most of them. And I'll show an example later where this turns out to be quite useful when implementing the equals method, which, as I said earlier, is quite complicated. So here's what the new instance of looks like. So we can say, instead of just saying if obj instance of integer, we declare a new variable following integer. So we say obj instance of integer int obj. And so if instance of is true, then int obj is a new local variable that's declared to be of type integer, and it's initialized to the cast from obj to integer, which is what we saw. This is all implicit. You do that all the time. You just have to write it out every time, but not anymore. And so there's some interesting and very complicated issues with scoping, but mostly, again, this is do the right thing. If obj is not an instance of integer, then that variable is out of scope and has no value. But if obj is an instance of integer, then this new local variable has its scope is the following block of the if statement. And so within the block, we know that int obj is an integer, and we can just go ahead and use one of its methods directly without any casting. All right, so here's a more complicated example. This is an equals method written in the old style, and it's a little complicated. I'm not going to go through this all, but basically we do an instance of check and we do an identity check, and then at some point you can see this is spread out a little more, but basically we're doing an instance of check and we're doing a cast. And so now if we've determined that the other object, which we're calling that, if it's an instance of this class, then only in the last statement of this method we can say, okay, now we're going to look at the fields and compare them and determine whether they're really equal. And so with the new instance of method, we can do our short circuit here with the identity comparison. But basically we say if O instance of this class, that, we put the declaration right there and it's initialized to the right thing, only if instance of is true. And so here's a little subtlety. That variable, its scope is for the rest of the Boolean expression, which is a bunch of complicated rules about here, but basically it does the right thing. So now that we've determined that the other object is an instance of this class, we can just go ahead and use it. And so we can really streamline a lot of code this way instead of having to write out a bunch of conditional expressions and stuff like on the a bunch of control structures and if statements like we did on the previous slide. All right. So what's going on here? So I clicked through a whole bunch of things, but this is all just individual features, right? It's like, no, remember I said at the beginning, these are all working together. So not only, it doesn't look like it, but these are all designed to work together. And so we are still working on some enhancements. One is adding type patterns to switch expressions, and that's something people have asked a lot about. And we can enforce exhaustiveness in a switch with sealed types. So let me click through these real quickly and then open for questions. Okay, so this is our previous example of seal interface shape. Now notice, shape, what I said earlier, shape has two implementations, circle and rect. So let's write a switch statement using this. So this is all future stuff. This is not in preview yet. But if we switch over a shape, we can switch on its type. So if it's a circle, we can call this method area of circle. And if it's a rect, we can call this other method area of rect. And we don't have to provide a default because we know, based on the declaration in the previous slide, that this is exhaustive. Shape can have only two implementations, circle and rect. So that's nice to know. So we don't have to provide a default case. But here's the thing. If we add another implementation in the shape declaration, then the compiler will check this for us and say, you need to provide another case here to handle that new one. 30 seconds on deconstruction. So the point of records being transparent carriers of data is that the compiler now knows enough about a record to extract its fields. So here's a variant of that where we know a circle has a center and a radius. And so instead of doing the instance of downcast and extract, we can write a pattern that declares variables that extracts them for us. And so, whoops, sorry, typo on the slide here. It should have been pi times radius times radius. But basically, if shape is a circle, we extract those variables for us, and those are declared as local variables implicitly, and we can just go ahead and use them. And same for the points of the rectangle. And here's another thing. Here's another example of a pattern. If we have a shape and we know it's an instance of a circle, we can ask for things to be extracted conditionally. And so if we want this conditional to be true, if we're dealing with a circle of radius 1, that is a unit circle, then we can do that conditional extraction in this expression. And so within the if statement, we know that that shape is a circle and its center is at point P, but we know that its radius is also 1 because there's some extraction of the radius there and matching to the constant that we provided in this pattern. And so within the if statement, we know that shape is a unit circle centered at point P. So that's a lot. This is all very new for Java. I don't think we even have compiler support for this yet, but this is our paper proposal. So here's my final summary. So I'll just leave this up for a little while so you can look at the links. There's the summary of the different features and when they're delivered. But I think if you want to find out more about pattern matching, there's this link in the middle of the slide to the paper by Gavin Bierman and Brian Getz, Pattern Matching for Java. That will go into a lot more detail about all the stuff that I covered in just 1 minute at the very end there. That's all very confusing if you've never seen pattern matching before. So if you want to find out about it, certainly go there. And also at the top is the link to the Amber project page. Most of these features are very well documented by JEPs, which are JDK enhancement proposals. I think that's the definitive documentation for these features, so that's the first place I would recommend looking. Go to the Amber page and follow the JEPs for each of these individual features there. There have been articles that have appeared in popular press, and sometimes sometimes they're good, sometimes they're bad. They can be variable. So I think the definitive place to go is the OpenJDK Amber page. And with that, I have reached the end of my presentation here, so I'd like to turn it back to Sharat and Venkat. We have a couple minutes left for questions.
Stuart, there are a few questions. I can read them for you if that would
Oh,
help.
yes, please.
Okay, so the first question I see here is, can I implement a sealed interface with Lambda expressions?
Good question. I would, okay, so first of all, this is under development now, so the answer might change. But as I understand it, I think the answer is no, because a sealed interface has to have actual type declarations in it, where a type declaration is a class or an interface. So the sealing is over type names. And so lambdas are not types. So I don't think that works. I don't know of a way to do that.
The next question here is, doesn't using instance of in an equals test allow for non-associative comparisons? It permits classes to be equal to subclasses, but not vice versa.
Right. Okay. Yeah. So that's an issue that I alluded to in there. There's a lot of there's a lot of discussion about whether you should use instance of or get class in the implementation of an equals method. And it depends on what you want to do, right? So in the presence of subclassing, that's where this issue arises. And so that's absolutely true. If you call get class and in your equals method, then you have your equals method has certain characteristics, but if you call instance of, then it has different characteristics. And so it's this terrible trade-off, which is you could, yeah, okay, so one way it breaks associativity, and another way it doesn't do a complete comparison or something. I forget all the issues, quite frankly. But I think the main thing is that for records do not allow subclassing. So we've cut off this entire issue. And so so anyway, yeah. So I think in fact one of my examples used get class. I think the conventional class used get class, but there was another example of equals where I used instance of. So it depends on what you want to do, but I think that the takeaway from that is records do not allow subclassing, partly for this reason, because subclassing just complicates all these issues. And you can, in fact, there's no right answer. The answer is, should you use get class or instance of? And the answer is, it depends on what you want to do.
Very good.
Okay.
I'm prompting people to post questions
okay.
On the chat if anyone has one. While we wait for another question, we got a couple of more minutes. I will ask you, Stuart, what's your favorite feature?
I think, let's see. I think records. Why did I mean? I'm a little. I'm struggling a little bit with why, but I remember in discussing all this stuff. It's interesting because initially I was opposed to var. Okay, so that's a secret that's out there now. And I wasn't opposed to it very strongly. I just thought that there were better things we could do. But after a bunch of back and forth, and this is something that people ask for a lot, it's like, okay, well, so we added var, so I'll use it, and it's useful. When looking at all this stuff, oh, this is kind of interesting. But when the records proposal started to come through, I thought that's really nice. I think what we need to do at some point is write out. I think if you go to the Amber page and look at the link to the records JEP, there are some interesting examples in the records JEP. In addition to, I don't know if the streams one is there, but the ability to create types very casually and have them be full featured is very, very nice, and that's something I constantly miss. So what I often do is if I need a little helper class, in the absence of records, I'll just declare a class. And it's like, well, I guess I have to write a constructor that initializes the fields. But then it's like, well, I don't want to write out the accessor method. So I'll just use direct field access. Or Well, do I need to write an equals method for this? Well, I guess this is just a simple little helper class. I won't bother writing an equals method because I know I'm not going to store it into a, into a hash map or something like that, just for this little thing, right? So you make all these shortcuts because writing a full-blown class is just so arduous. So you saw that two-column example where it equals hash code, toString, all this stuff. And then of course you're debugging, you print something out and you get this, you get the garbage version of toString from object. It's like, all right, so you go back and clutter up your code some more by writing a toString method. So anyway, so that's my answer for why I like records, right, is my favorite upcoming feature.
Sounds good. We have one question here. Would if or try statements as expressions ever come to Java?
That's an interesting question. I know we flirted with that a little bit. There's this idea in programming languages that there's no difference between a statement and an expression. So for instance, Lisp is that way, right? Everything is an expression. And so there's some things that do control flow in Lisp that look like statements, but in fact, everything returns a value. And I guess Scala is that way, and maybe Kotlin, correct me if I'm wrong. But so we've toyed with that idea, but it actually creates a lot of complication. One of the things that does catch people is that there are you might accidentally leak information about if you have, so for instance, well, so this is a weird example. I don't know if anybody remembers JavaFX script, which was the scripting language that JavaFX was originally based on before it was all converted to Java. That had an unfortunate, well, in some ways it was nice. It was you didn't have a return statement. You had a function that had a sequence of statements, and the value of the last sequence was the implicit return type of the function. Unfortunately, the return type of functions was also inferred. And so that actually leaked, the type of the return value leaked into the public API. So if you made what you thought was a change to the implementation, you could actually change the type declaration and make an incompatible change by accident. And so we've flirted with this idea. Sometimes people ask about it. In fact, there was a Twitter exchange just today about, oh, why don't we have a new statement that is just a sequence of statements that returns a value? So, so it comes up from time to time. I don't think it's likely. One thing, if we do get to that point, I would say that we would not want to have an expression. We would not want to have a statement that basically returns the value of an expression. We would want to make some more fundamental change to the language where all statements had return values, or make something that was much more general than that. But there you have to understand, what are we trying to do and how complicated would that make the language, and what changes would that make? Because there are a lot of things where a statement is just a statement and there's no value there. And so how you would deal with statements that now suddenly return values would be an interesting complication. So I think it's not a bad idea by any means. But there's a lot of complexity there, and I think one of the things that we look at regularly is how much value does it add to the language to add something like that. It certainly makes things more orthogonal, and in some cases it makes things more useful, but there's a lot of complexity there that needs to be overcome. So it's a cost-benefit trade-off, basically.
Well, certainly exciting times for Java, and I really want to thank you, Stuart, for taking your time to share the knowledge with us. I really thanks for everyone who's joined, and especially for your time as well. I'll hand it over back to Sharat.